Okay, let's get started. So, this is just an overview of how you can possibly maximize your score in the exam. Okay, and this is really how I grade, and other professors might be grading slightly differently, but more or less, if you have these things, usually you get a lot of points. So, draw free body diagrams. Okay, I like to give like 20 to 30% depending on the number of forces on the free body diagram. So the second thing is we want to see if you are able to understand what we have posed in the word problem. So it could be, we could ask you velocity when the time is so and so, or velocity when the distance is so and so. So we want you to figure out what concepts you'll use to solve the problem. So it's key that you identify the concept, put it down in writing, principle of work energy or conservation of momentum or equations of motion, and then set up the equations. Okay, writing F equals ma, writing moment about point O, these things carry credit. Okay, don't just jump onto writing the equations. If you write the equations correctly, we usually give you a lot of points. So that's the key. And then when you write down relevant equations, okay, credit is for correct sign and values. Yeah, so when I'm looking at your setting up of equations, I'm looking at if you've set up individual components, right? So there'll be partial credit for putting all the things together. So if you have the moment due to mg, is that right? Is the sign right, and so on. So it's just, don't just put random signs. What you put there is important. But clearly, if you put things down, the numeric value or the symbolic value mg cosine theta, that carries credit. If you just put mg when the actual force should be mg cosine theta, for example, then you'll get points deducted. And then final answer, which is also important but not too important, is it usually carries minimal weightage, 10 to 15%. So if you're in crunch for time, what I recommend is doing 1 to 3, and you can do 4 last. So I think that if you want to maximize your score and pass the course, some of you want to pass the course, right? You're taking it more than once, and you want to just get done with this class. I would highly recommend that you draw free body diagram and write a relevant equations. And I think that if you do those two things, then you can pretty much be certain of getting 50% of the points. But you can't do that unless you study everything, right? You need to understand which concepts to apply on which particular problem. So previous class, so the people who are not here, last class, I showed you.
I have a question here.
Yeah.
A lot of what you said I do in my exams, but I don't know somehow when they grade it like really, like if it's from 10, if you have body diagram and stuff like that, they would give you like 3 points. Like I'm talking about exam 4.
I don't know how they grade exam 4, but I typically try to give like, I look at the free body diagram and I say, did you draw, if there are 4 forces, right? I would give you 4 points for the 4 forces, showing those forces correctly. Sometimes we have to stretch those points, give you more than 4 points if there are 4 forces, depending on whether those forces are tricky or not. So, for example, friction, if you show the right sign, right direction, or right magnitude, right direction, then you get points. So, as I said, it varies across instructors, but nevertheless, it's always a good idea to draw free body diagrams.
So will we be able to like request a regrade for the final?
For my section, yes, because I'll be using Gradescope.
Okay.
And I'll be posting your grades just the way I post. But I think other folks, you'll have to go to their offices. So yeah, so you should be able to do it without, if you leave town, you should still be able to do it because it'll all be on Gradescope. So this is basically the algorithm I suggest if you're trying to solve a problem. Essentially follows an elimination approach. You start off figuring out if it's a kinematics problem, which is chapter 12 and 16. If not, then you try to identify if it's a problem where you can use conservation of energy, which is chapter 14 or 18. If that doesn't work out, then you figure out if it's a problem where you can use the principle of impulse and momentum. Okay, and if that does not work out, then what you're left with is only F equals MA, which is 13 and 18. Okay, this I've already posted, and if you've missed this class, I recommend you go through this. I talked about this. I posted my lecture notes, a video of the lecture, so you can also go through that. But that's what we want you to be good at, which is figure out what sort of concepts you can use for given a problem. So what I'm going to do is I'm going to just continue solving problems. Somebody suggested that I should have in-class quiz. I'm not going to have in-class quiz today or tomorrow. I realize that some people don't want to come in the last week. They want to maximize their time studying at home. That's fine. What I'll do instead is the problem with the software iClickers is that at least I don't know how to eliminate 5 worst exams, throw them out, and give you points for that. I wanted to eliminate some quizzes, but I can't do that. I don't know how to do that. What I'll do instead is, so 5 quizzes is 10 points, right? Instead, I'll give everybody 10 points. So that is better than giving best of 5, which means that if you actually scored 100 on 100 in all the quizzes, you'll actually end up getting 110 points, which means that you'll score, that's 10 points basically equals 1 point in your finals. That's what it is. That's what I'll do. It's much easier for me to do that. Okay, so we'll just go along this. One more thing, we have not yet set the exam. We talked about it, but we've not set the exam. So we'll do that tomorrow. So after that, I have a better idea on what is an exam, and our practice questions will try to reflect what's on the exam. To some extent, we can't just give you the problem which will show up in the exam, but we'll try to see that it reflects in the practice exam. So more or less, the quorum is that we're going to try to test you on what we've put in the term exams, homeworks, and practice long answer questions, which you've already had for the term exams. Now, it won't be the same problem. It could be the same problem, the same figure, but different things might be asked. It could also be that the concepts might be picked from there, but it might be a different figure from the book. We will clearly not, most likely we will not have all questions from term exams and practice exams, because we want the people who've worked really, really hard to get full points. So it might be 60% to 80% from the term exams. Again, don't hold, this might change. I will know only tomorrow after we set the exam, but I'll let you guys know what happens on Wednesday. And then we've not posted the practice exam just because we want to give you a better practice exam which will reflect the final. So I'll give you more details on Wednesday. That will be the last class. Okay, so let's try to sort of use the algorithm or that elimination approach which I talked about to solve some problems today. Okay, the 15 kg block starts from rest at A and is lifted friction free, so there's no friction, with a force F equals 500 newtons. Spring constant K is 10 Newton meters, is attached to block A. The spring is unstretched when the spring is shown at the rest position, so rest and spring is unstretched. Assume the value of G equals 10 meters per second square. Draw FBD of the block A and determine the velocity of block A when it has traveled up by a distance of 1 meter. This was a question in the last exam, but not last exam, I mean last semester. The other instructor gave this problem, so I thought it was a good problem, so I'm doing it. Okay, draw free body diagram. Okay, so friction free. What are the forces on the block A? Now, when you're drawing a free body diagram, don't draw it for the position shown here, because the force from the spring is 0, right? The force is what? K times the stretch, but the stretch is 0, so the force is 0. Don't draw it for that. Draw it for a generic case when this has moved up and the spring is stretched. So clearly there's a force due to the spring. Okay, what else? Normal force. Okay, it's not clear which direction it's going to be. I think it's going to be the other way, but you could draw it this way. There's tension, and that's going to be at an angle. And what's the tension? Sir? Yeah, it's F for 500 newtons. And then what else? Is that it? Okay, remember there's gravity. Okay, that's it, right?
So in this case, you assume that normal force is this way, but you don't know for sure.
No, I think, okay, so I assumed it this way, but actually it'll turn out to be this way, right? Because when you take F, you resolve it, that F is theta, so you see that F sine theta is n. But yes, of course, you don't have to draw it in that direction. You can show it this way, and the sign will come out to be negative. So that this is a valid free body diagram. If you drew it another way, that is a valid free body diagram. For the things which you know the direction, you should put the direction. For things you do not know the direction, don't put it. So if you drew mg upwards, that's wrong. Or if you draw the spring force downward, that's not right. You should draw it in the right direction because it's a known quantity, sign as well as magnitude. Okay, anything else? Okay, so that's the free body diagram. Next is determine the velocity of block A when it has traveled by a distance of 1 meter. Okay, so when you have this problem, then I would recommend going through the elimination approach, and I'll go through that because some of you were not here. So the first thing is, if you ask to find the velocity and acceleration of a point, when the velocity and acceleration of some other point is given. So in this case, you're given a force of some point, right? But you're not given the velocity. So if you're given that the spring is moved down with the velocity, then yes, it's a kinematics problem. But in this case, you're given a force. So this is not a kinematics problem. If you're asked to find velocity when the object moves a certain distance, or vice versa, so v as a function of distance or distance as a function of v, then it's recommended that you use conservation of energy, or if there's a non-conservative force, then you use principle of work energy. So it actually fits this category because you're asked to find velocity when the block has traveled a distance. So v is a function of d. Okay? So when you have that, there are two choices: conservation of energy and principle of work energy. What do you think I should use? So in this case, actually both work out, principle of work energy as well as conservation of energy. The reason is F is 500 Newton, right? When the force is a constant, that actually is a conservative force.
So typically, conservation energy when you use it is easier.
It's not necessarily easier.
Not necessarily.
It's the same. I would just say that actually you can, even if it's a non-conservative force, you could use conservation of energy by accounting for the dissipation. There's a place to put dissipation. It's not necessarily easier. I think it's more intuitive to use conservation than to use principle of work, because you know that energies cannot be destroyed. Energy here, position 1 is energy at position 2. So yeah, for some people, yeah, it's easier. You could use either one this way because F is constant, so it is actually a conservative force. So only force which could be non-conservative is F. Now F is constant, so it is, if F was say a function of theta, then it may not be conservative. A conservative force is the one in which the work done depends only on the final position. It doesn't depend on the path taken by the particle when the force is applied. So we could use either method. Let me just, I just chose to use principle of work energy. So let's see what's asked. So we're given that velocity, let's call this position 1 is 0. The distance is, so let's measure distance this way. Y is 0. We want to find the velocity. Let's call that 2. When the distance covered by the block is 1 meter. Okay, so since F is constant, is F is a conservative force. So let's just use principle of work energy. Okay, this principle is recommended when the forces are not non-conservative. So if you do not know that F was conservative, then you can always use that. It's a safe way to solve a problem. This is safer than conservation of energy because it accounts for non-conservative forces. So principle of work energy says that the kinetic energy at position 1, which is here, plus the work done by all the external forces equals the new kinetic energy. So if that's 1, and then this is position 2, it's 1 meter, right? Moves distance of 1 meter is equal to t2. So t1 is 0. u12 is going to be the work done due to all forces acting on the particle. Okay, and we are interested in well, there are, if you see this, there are four forces. So there is mg, uh, acting about for a distance of 1 meters. The question is, what's the sign on the work done due to that? Let's see. So mg is down, and the block moves up. So yes, it's negative. So then we have F spring. Sorry, this will be half K times 1 square. Right? What's the sign on that? Is it positive or negative?
Negative.
Yeah, so the work done by a spring is always negative. And then the final one is due to, well, sorry, there are two more. There's N and F. What's the work done by N? Capital N.
0.
It's 0 because N is to the left or horizontal where the displacement is upward. So the work done, what is work done? It's force times distance, right? But F, it's F dot S, the dot product. But when you take a dot product, it's the cosine of the angle between the force and the displacement. But since the cosine of the angle is, well, cosine of 90 is 0, the work done is 0. Yeah.
In other words, if there's a force acting on a body, but that force does not move the object per se, like it does not move it in a path or it doesn't affect the path, then we don't take it into account.
No, so we should be careful there. If the force is 90 degrees to the displacement, then the work done is 0. When the force is not 90 degrees, like what's the work done by capital F? So displacement is vertical, but F is not
Right.
at along the displacement. It is at an angle, but it still does work because work done depends on the angle between that. So the work done. So the last part is actually the work done due to force F. So F cosine theta times the displacement. And I think I need to integrate this. Yeah. This is, so F cosine theta is F in this direction, dy is in this direction, so it's positive. And I need to integrate this from y equals 0 to y equals 1 equals half mv2 square, which is the final energy. Okay, so I guess these are all easy to evaluate, right? this is easy, and this is unknown. Okay, we have to evaluate this. I'm going to try to do this separately here. Okay, so f is a constant, right? That's 500. So we can pull that out. How do we integrate cosine theta times dy?
Become sine theta, d theta.
No, if it was cosine theta d theta, yes, you could do that, but there's cosine theta and there's dy. So the question is cosine theta constant? When
With respect to y, it is.
Well, no, because the
no,
angle is changing.
the angle is changing. So the angle theta is a function of y. You see that? This is y. This is y. Right? As the particle A moves up, the angle theta increases. So you cannot integrate that unless you try to find y as a function of theta, and then you got to sub that in. So what you can do is you can see that my bad. This shouldn't be y. Y is the motion from here. So this is theta. This is 1. Okay, and you're also given that this is 1 meters, right? So this distance is 1. So if the particle moves by distance y, so it's initially here. If now it has moved a distance of y, then this is going to be 1 minus y. You got to draw this figure for a generic angle theta, not at the special case. The special case is when the vertical distance is 1 and horizontal distance is 1. But you got to draw it when you got to write like the free-body diagram when it is at a generic angle theta. So if you look at this figure now, you can see that cosine theta is what? 1 minus y divided by square root 1 minus y square plus 1 square, right? This is the hypotenuse, and that hypotenuse is here. So this comes out to be f so now you can integrate it because
I don't remember how to integrate that.
right.
So process.
Okay. If something like this comes up, feel free to leave it as it is. So what happened in that exam was the professor gave this question, he graded it, and I did not see the question, and then he graded it, and nobody. It was a class of 60 students. Nobody saw that he made a mistake. He basically assumed that theta was a constant, and he integrated that. And then I told him that's wrong, and then I don't think he regraded it. But nobody came to him and said that's wrong. It was a question in the exam, but he did not intend to give such a hard question. If something like this comes in the exam, then you can keep it that way. It's absolutely fine. We will not penalize you for not remembering how to integrate that. But anyway, nevertheless, you got to find that work done, sub it in here, and then solve for V2. Let me just finish it off later on, but what you get is
Remind me of the problem where you had like a wheel with paint through it, and it was pressing against the piston.
uh-huh.
Then you'd have to come up with a formula like
That's right. That was
R plus.
right. That was a question I think on the exam too, right? A similar question was in the exam.
The short.
Yeah, but then for those questions, I think we asked you to find a formula. We didn't ask you to do an integral. So I'll solve this later. Post. Did I do this problem in class? I didn't finish it.
Yeah, you did.
I did this. So let me just briefly talk about this. I will not solve it. I'll post my notes. The reason I'm showing you this problem is because a question like this in the exam is going to be, you got to figure out how do you solve this, right? Because you don't know which chapter it comes from. Let's read through this, and then there's another problem which is based on a similar figure, but I've tweaked it a little bit. So let's just read this. The 5-pound cylinder is falling from A with a speed of 10 feet per second onto the platform. Determine the maximum displacement, let's call it Y, caused by the collision. The spring has an unstretched length of 1.75 feet. So the unstretched length of the spring is 1.75 feet, and it's originally kept in the compression by one foot long cable attached to the platform. Neglect the mass of the platform and spring and any energy lost during collision. So this block falls on the platform. Now what they've not told you, but assumed as that the block sticks onto the platform, and then the whole assembly moves together. You will find the maximum compression of the spring.
That is 2.
What's that?
So the compression on the spring would be
0.25 for the displacement currently would be.
You have to find how much the spring is and the block that compresses, how much goes down. It starts off being compressed, but it gets further compressed because the block falls around.
In its initial position, we would write it as already being displaced by 0.75.
That's right. So the energy stored in the spring is going to be 1.75, sorry, 1, the stretch length, minus the unstretched length, so 0.75 squared for the energy. Now for this problem, you're told to find the displacement and there is no energy loss. Right? What happens basically is that when there's maximum compression, the velocity of the complete assembly is 0. So in effect, they're asking you to find the displacement when the velocity is 0. So when you see velocity and displacement, you got to use either conservation of energy or principle of work energy. In this case, there is no dissipation, there's no non-conservative force. So you could use conservation of energy. The good thing is that you could actually take the energy at point A and take the energy when the complete assembly is fully compressed, equate the two, and that will give you an answer for the displacement. Okay, I've done this. I'll post my solution to this. I just twisted this problem a little bit. Okay, so same figure, but slightly different. So 5-pound cylinder is falling with the same speed, onto the platform. Determine the maximum displacement of the platform caused by the collision. The spring has an unstretched length of 1.75 feet and is originally kept in the compression. So it's all same till there, but there's a slight twist, which is the platform, this thing, has a mass of 1 pound, and the mass A stays put on the platform after collisions. The only difference I made was that I said the platform has 1 pound mass. It's not massless, unlike the previous problem. So A collides. When it collides, it sticks, and the whole assembly moves down as one single assembly. Okay, now how do you solve this? Well, it's not a kinematics problem, right? Because the collision involved, the spring force involved. Can you use principle of work?
So you consider it a rigid body?
It is not a rigid body. It's basically a particle problem. So you are told to find the same thing, which is you're going to find the velocity when the displacement is. You're going to find the displacement, the velocity is 0. However, you cannot use the principle of work energy here because there's a collision involved. So actually, this is a mixture of two concepts. What you need to do is you're going to.
So can you use impact?
You have to use impact, right? Because it's a collision. So what you need to do is you're going to break this problem into 3 parts. The first part is find the velocity when the block is just about to hit the platform. How do you do that? Use principle of work energy.
You stop the calculation at the.
Yes. You stop the calculation right here first. Then there's a collision between the block A and the platform. So there's a way in which you can find that, right? There's a coefficient of restitution is it's zero because it's a plastic collision. So if you use conservation of momentum, and thereafter when it hits the block, it becomes one single assembly. That particular assembly is going to have a new velocity. We got to find that velocity, and then we got to find the displacement due to the whole assembly moving down. So then we have to again use the principle of conservation energy. But this is, I think, the key thing, which is here it's not just one concept. You got to break it down and use multiple concepts to solve it. So that's the other kind of problem you might get in the problem, which is it may not be cherry picked from a particular chapter, but it might be mixed. There'll be a mixture of problems. There are other problems, I think, in this section, which is an example would be, if I remember right, there's an inclined plane, there's a particle which is sliding, and then it is airborne, it falls down. That's a problem. But I think that the problem in the homework was there's a cannon and the ball fired and it bounces, right? So that's a problem where they've combined projectile motion with collisions. So you got to be aware of those sets of problems.
The cannonball bouncing was something they accounted for in the Napoleon era to try and get extra distance out of it to devastate enemy ranks.
Yeah,
I'm not a history reader.
I see. Okay, so let's try to solve this.
Would it change if it were said that something smacks it downward? Would it change?
You mean a force?
Yeah, like someone just had a stick.
Yeah, that's. I think there's a problem in the book about somebody hitting a nail with a hammer, and then you got to figure out how much the distance the nail travels. That's also a good problem. Yeah, you should probably put it in the exam. Okay, so let's solve this. So we got to find the displacement when the velocity is zero. So let's divide into three parts, which is A, B, and C. So the particle moves from A to B, B to C. Okay, let's do from A. You know what? Let me write this as 1, 2, and 3. So from 1 to 2, one way you could do it is use the principle of conservation of energy. The other way you could do this is it's a particle falling under gravity. So it's a kinematics problem. So V at 2 square is V at 1 square plus 2g y. Velocity of 2 is unknown. Velocity at 1 is 10 square. Gravity is 32.2 and displacement is 3 feet, and then the sign. So gravity is downwards positive, y is downwards positive, so it's positive. So if you do that math, you get V2 equals 17.1 feet per second. So now the block is right here, but it has not collided with the platform. We got to figure out what happens when the block, which is moving at 17.1 feet per second downwards, what will the velocity be of the combined assembly when something which is stationary collides with something which is moving? So we got to use, so at 2, we got to use principle of conservation of momentum, which says that m1, so I'll write m2 let's just call it A, let's call this B. So mass of A time velocity, I'll call it V2A, indicating that it's velocity of velocity of A at instant 2, but before impact, plus mass of B, velocity to B equals mass of A, velocity of 2A, and I'll put a comma. apostrophe to indicate that it is after collision. MBV to P. These are velocities. Sorry, my bad. This shouldn't be so. They move with a. So since the two blocks stick, right, and move as a single assembly, they'll have a common velocity. So I should just write it as MA plus.
I have a question. How come like the momentum is conserved when there's like a spring force?
Yes, good question. Let me answer that question.
Okay.
V2 prime. Okay, so good question. So if there's a force from the spring, how can if you draw a free body diagram of this, block, the force, there's the impulse, the same impulse, and then clearly there's going to be a spring force or spring impulse. Spring impulse. Okay, this is the force because those two particles are hitting. Now we make an assumption here. We make the assumption that the impulse due to a spring. So what's an impulse? It's basically force times displacement, right? So in that short span of time when the collision happens, the spring is not displaced. When the spring is not displaced, the force is going to be zero. So it's an assumption. In reality, no, there'll be slight displacement of the spring, which means that there'll be a force.
The question is when the spring is stretched or shrink by some distance.
No, so initially the spring is compressed.
Okay.
Okay. Now when this block hits this, it becomes it becomes a single body because it sticks onto this, or there's a plastic collision, and then the whole assembly moves down.
So there will be no change in spring?
There would be a change, but afterwards. Now, we are breaking this problem into three parts. First part is when the block comes and is about to hit the platform.
Okay.
The second part is the block hits the platform, the block sticks onto the platform, and that combination has a velocity, a common velocity. Thereafter, the whole thing moves down, and the spring is pushing upwards. So I'm at the point where I'm trying to analyze what will happen if the block sticks onto the platform. When it sticks on this platform and the block, is going to have one velocity. I didn't find that. I thought your question was what happens to the force due to the spring. The force due to the spring is negligible during that instant when the collision takes place, because we assume that the time for the collision is infinitesimal, and so the spring is not compressed. So there's no spring impulse.
So this is similar to the one when they shoot a bullet into that piece of wood. The one you did in
Yeah.
Same thing.
Yes. Yes. So yeah. So MA V2A plus. So this is the velocity after collision. So the mass of A is 5. Velocity of A is 17.1. Found. Velocity of the platform is 0 initially, equals the combined mass 5 plus 1, and velocity 2 is unknown. Velocity of 2 prime is equal to 14.25. So what you notice is that because of the collision, the velocity of the combined assembly has decreased from 17 of the mass to 14.25 of the combined mass. So that's what momentum does. Collision does. It dissipates energy so that the velocity is reduced. So the last part is from 2 to 3. So now it moves from, this combined assembly moves from 2 to 3. We're going to find what's the displacement. Now you could use this. So the collision event is past, and all the forces are conservative, and so you can use the conservation of energy from 2 to 3.
Also use it for step 1.
We could use it for step 1, just that I noticed that it's just a particle falling under gravity, so it's much simpler. But if you use conservation of energy, you will find that you get the same equation. Mass and mass cancels off. That is actually, this equation is actually conservation of energy. If you multiply with half m, you get initial energy, final energy is initial energy plus potential energy. Okay, so T1 plus V1 equals T2 plus V2. Initial energy is half MA plus MB V2 prime square. The initial potential energy is, so this is the energy stored in the spring, right? So half K times 1.75 minus 1 square, right? Because 1.75 is the, should write it. Let me write the other way so that it's consistent with what I've said, which is the stretched length minus unstretched length squared, and it's positive or negative. What's the potential energy to a spring?
Positive.
It's positive. Okay, so that's one. But then there's also energy due to
Well, if it's opposing the motion of the particle,
no, that it's not a it depends on that. It just depends on the stretch. Okay, so we also need to choose a datum because there is a potential energy involved due to gravity, right? So we can choose a datum here, or we can use a datum when it is fully stretched, fully compressed. So let's use that as a datum. So fully, so datum is when the spring is fully compressed. Okay, so one of the energies will become 0. You could also use that as the datum. So that's going to be MA plus MB, gravity times the displacement, which is going to be Y. By the way, is it positive or negative? If the datum is down and if the particle is up, then what's the potential energy? Sorry, yeah, what's the potential energy?
Positive.
It's positive. So that's positive. Equals the final kinetic energy, which is going to be 0 because it comes to a stop. And then final potential energy, which is also going to be 0. Sorry, it's going to be 0 for the gravity, right? Because our datum was when it's fully compressed. But then there is energy due to the spring. That's going to be half K times the stretch of the spring. So what's the stretch of the spring?
0.75 plus displacement.
Yeah, because this is 0.75, right? This is one, the unstretched, this is y, so it's 0.75 plus y, this is net stretch. So in this equation here, V2 is known, this is known, this is known, that's known too, y is an unknown, so we have to solve for y. So this will be a quadratic equation because you can see there's a y and then there's a y which is squared, so it's going to have a y square term. And so when you solve for y, you get two roots. One of the root is negative, the other root is positive. It's 0.06175 feet.
So could we have solve-based using conservation of energy from 1 to 2 and then I guess something else from 2 to 3? Or that would be.
So this equation is actually the same as conservation of energy, 1 to 2. From 2 to 3, yeah, I did use conservation, but this is the piece which is vital, which is what happens when two masses, so this is like a head-on collision. One mass is at rest, another mass is moving with a speed. Now they collide and they stick. So you got to find the velocity of the combined system, and that can be done using conservation of momentum. There's no way you can escape the conservation of momentum in this. If you do not use that, then it basically won't make sense. In fact, the previous problem, when the platform didn't have a mass, that's a problem where there is no energy lost due to collision because there's no mass, nothing to collide to. You just the mass is hitting into something which is massless, in which case its velocity will carry through, and in that case you don't have to apply to. So actually it turns out that if you solve this problem, the previous problem, this one, you get y to be 0.075. Okay, and if you see the y over here, it's less, 0.06175. And the reason why it's less is because there's energy loss due to the collision. So when there's energy loss, clearly the displacement is going to be less.
The way you have it written, it's when we're doing the work in that chapter, we always have to assume that the plate had no mass, or just full to ignore it. But on the test, do they have to solve the mass of the plate?
Well, it depends, right? I mean, I'm not too sure how I can answer that question. We should have a problem where there's collision. It's not clear if you're going to have this one or similar. But the problem about there's a very famous problem, and this usually comes, I don't know if you know an exam, where the hammer has it's dropped, so it's a fixed joint, and then so it's a pin joint, and it has got its inertia, and so you got to analyze the system when it's released from, say, from the 90-degree angle, and then it hits a nail. So you got to first use the rotation about fixed axis. You got to use the conservation energy, which is a rigid body. If you use that, and then it has some velocity, find the velocity of that, and then you got to figure out what's the velocity imparted, and then it's a mixture of principle of F equals ma and collision, and I don't know if you have that question, but that's one of the favorite questions in many exams. You see that question showing up. Okay, so I'll see you on Wednesday. It's the last class. Hopefully, I'll give you some hints about the exam. We'll post some practice questions. I'm going to tell you the room, and it's not in the same room, by the way. It's a different room. We'll be in touch through emails. And I'll have office hours today and tomorrow, 11:30 to 1, 80 2.338. I'll have office hours next week too. I'll announce them later on.
Sir,
Yeah.
is that on the